Circular motion with variable speed is what we observe in day-to-day life. So we have not only change in direction, but also change in the speed, change in the magnitude of the velocity. So that's what we're looking at. That's the case. So when it comes to varying speed, we need an additional acceleration, and that's the second thing that we are getting introduced to. So acceleration in case of a non-uniform circular motion is what we are trying to understand. See, we already know one force. What is that force? We know our central seeking force, which makes the object go. Sorry, I don't know, it's not writing. Okay, just a second. Yeah, I just wanted that. So this is your central seeking acceleration. The acceleration which makes the object go to the center of the circle per se is your central seeking acceleration. Now, we are looking at the rate at which this particular object moves. For example, over here, it's moving at this rate. Now, if I make it faster, say it's moving at that rate. Now I'm changing it again. Now it's moving faster, right? Faster again. So this is increasing the speed. So we are increasing the speed, or we can even reduce the speed. We can make it go slower. So these are all account of change in the rate at which it's going round and round. So to account for this part of changes as well, we need another velocity, and that is your and that is your tangential component known as tangential acceleration, right? So we have tangential acceleration. When an object's speed changes while moving in a circular path, we need tangential acceleration in addition to centripetal acceleration. So we need both. So tangential acceleration, you have A and you write T at the bottom. So it's actually small t. And that is how we represent tangential acceleration. Oh, no, wait, it's capital T itself. Okay, so that's how we represent tangential acceleration. It changes that is tangential acceleration changes the object speed and is always directed tangent to the circular path. Now, we have two acceleration basically, right? So end of it, we have a total acceleration. So the resulting acceleration is a combination of these two accelerations. So this is pointing towards the center. So this is the radius. So if you guys remember, if you consider a circle, if you consider a radius and a tangent drawn to that, the angle between them is 90 degree. So these two are perpendicular to each other. These two angles, those two vectors are AC and AT are perpendicular to each other. So this being the case, if they are perpendicular to each other, the combination of these two perpendicular components, when considered, the resultant when considered, will be pointing somewhere in this direction, right? We'll use the parallelogram of vector addition. So we have something like this and something like that. Let me do it another layer. I'm drawing a parallelogram. So our resultant will be the diagonal from here till there. So that is your resultant acceleration. So A square is equal to AT square plus AC square. This comes from our vectors. So I'm not going to explain this over here. 0.5. So that's your total acceleration, resulting acceleration. A combination of two perpendicular components, centripetal acceleration and tangential acceleration, changes tangential acceleration that changes speed and direction. So that is given by this, that's the magnitude basically. And you have AC plus AT. Okay. That's your A. Okay. Now that's your mathematical expression. Now let's get an expression for your tangential acceleration. So tangential acceleration is changing the velocity. So the average tangential acceleration, guys, it is capital T in your book, so I'm using capital T, but I have typed here small t, so keep in mind whatever your book is telling, you guys do that. It's just a symbol, so whatever is being asked, you use that, so don't think too much into it. So it deals with your change in velocity with respect to time, right? But we know that the velocity is equal to omega r. So therefore we have change in omega into r by delta t. But r is constant. So delta omega by delta t. But delta omega by delta t is what? This is nothing but your correct. Another acceleration. Oh, sorry, you don't know that. No, my bad. Oh, you guys are still over there. No, let me just do this. Okay, then applying limit delta t tending to 0 on both sides. Let me not do that for you guys. Sorry, I need to define this actually before my sequence is a bit off, my bad. So guys, yeah, let me introduce this. Delta omega by delta t you not yet come across. What is this? What does it tell? Let's have a look. This is what? Change in correct angular velocity. And the bottom one is change in time. So change in angular velocity by change in time gives us what? It's the rate of change of angular velocity. That is your angular acceleration. My bad. I was trying to tell angular acceleration. Okay. So angular acceleration is nothing but your alpha. Okay, guys. So in this case, it will be r times of delta alpha. Alpha actually, not delta alpha, sorry. Alpha, average alpha. So this where alpha is your angular acceleration. Angular acceleration is nothing but the angle change of rate at which the angles are changing basically. This comes into picture only if you have a non-uniform motion, circular motion. If not, all of this will not come into picture. Okay, so I just took a second to realize that you are not yet introduced. My bad. My flow was off a bit over here. So if not, it's the same funda. We have tangential acceleration changing the velocity. Velocity in a circular motion, linear velocity is related to your circular, changes, omega r and all of that. So delta omega into r will come out. So we have delta omega by delta t. Delta omega by delta t can be defined as, yes, delta omega by delta t can be defined as alpha, right? So for instantaneous case, you have AT is equal to r into alpha, as simple as that. Okay, so generally they write like this. Okay, so that was your case of non-uniform circular motion. So circle with varying speed is your non-uniform circular motion. So here not only the angle, the direction, but also the speed is changing. To account both, we have two different acceleration that we consider. Again, we are dividing and conquering over here. So one is your tangential acceleration, another is your centripetal acceleration. Actually, there's a single acceleration. All the time there is single force. Guys, every time net force is the only thing that matters. Okay. But to understand, for our convenience, we have divided into centripetal force and tangential forces. So centripetal acceleration and tangential acceleration. So tangential acceleration, mathematical expression looks something like this. Right? And yeah. So I've written it here as well. And we have a new term introduced, angular acceleration. It is the rate of change of angular velocity. Okay. So that is over here. Right? I think you guys can start with this too. You need to know total acceleration as well. You need to write this. The mathematical expression, the drawings are over here. So this we are adding using your parallel law of vector addition. Then you have your expression for tangential acceleration. For that, I need to come over here. And finally, I introduce a new term called as angular acceleration.